Alright everyone, so welcome back to my channel. So today I'm gonna solve a problem called sliding puzzle, and this is a hard problem. And if you're asking why I have these number, because I use an extension called LeetCode difficulty something. So that extension is pretty cool. It shows you off how hard it is. So 180 is not really super hard questions if you understand the question. So anyway, on 2x3 board, there is 5 tiles labeled from 1 to 5 and empty square represented by 0. A move consists of choosing zeros, so you're holding a 0 and move it 4 direction and swapping with it. The state of the board is solved only if the board is look like this. So 1, 2, 3, 4, 5, 0. So if I draw that out, so 1, 2, 3, 4, 5, 0. So this is the complete board. As you can see on this example, you only need to move 0 to the left of it, and then you will have a complete board, right? So just swap these two together, you will have 5 and 0. So that this is our complete board. Given the puzzle board, return the least number of moves required so that the state of the board is solved. If it is impossible, we return -1. It is impossible if, let's say, we try all of our possible way, right? We move the 0 up or right, down, whatever direction that we have, and at the end we don't have any more move, we just return -1. So for this one, this is a graph problem, right? Because you have to move this starting point up, left, right, left, down, and a specific algorithm I'm gonna use for this is gonna be BFS, right? However, regular BFF will not gonna solve this problem because, let's say we have our visit set, right? We move our 0 right here to the left, right? And then this one is not the path that we want, so we want to move back. So we want to have the ability to move back, backtracking on what we are here, and then go up or left, something like that. So I will call this modify BFS where it have a state. And then we would add the state of the board with, I think also with the index of our 0, right? Our current index with the state into our visit set when we are using our BFS. So now what is gonna be our state, right? Our state is, luckily, there's only the 2x3 board, right? For us, the state is gonna be the 2x3 board, right? 2x3 board. Let's say we found again 1, 2, 3, 5, 0, something that looked like this, and we found this in our visit, and we found also the index of 0 in here, right? It means that, oh, we have this path going already. So that is where we are gonna use our board. I'm just gonna convert my board into the one-dimensional array. So it's gonna look exactly like this. So 1, 2, 3, 4, 5, 0, right? And let's say our 0 right here is a 6, right? Oh no, my bad. The index is gonna be 5. Let's change the color as the index of 0 is fine. So how do you know if you move up or left or right or down, whatever it is, to find the trying to find a neighbor to add to our queue in our BFS, right? So this is 0 right here, but luckily for us, we only have a 2x3 board. Because this is 2x3, we can manually set up the direction, right? How we can set up the direction? Let's say our board is our 0 is in here, right? We know that this one is only going down. At this point, right? At this index, which is right now is index 4, we know that we can go up, we can go left, we can go right, So index 4 in the direction, right, would have an array of index 0, 5, and oh, not 0. It should be 1. So 1, 5, and 3, right? So we can manually set this up, and it's only like 0 to, oh, hold on, 2, 3, 0 to 5. There's only 5 values in there, and we just manually just set up that mockups look like this for the direction. So it will be more clear when we hop on the code. So I would just do it and see how stuff go. Okay, since we are using the 1D array, right, one dimension array, our final state would be equal to 1, 2, 3, 4, 5, 6. Oh, 5, 0, right? This is our final state. Imagine just this is a 1D array. So we also have our direction, right? We manually set that up. So 0, from index 0 we can go down to go to your right, index 1, and go to down here. So this is index 3, right? Index 3. Same thing with 1. We just manually set up. So in 1 you go left, right. So 0, 2, and 4. 2 is gonna be 1 and 5, right? 1 go to the left, 5 is go to the bottom. 4 is, 3 is go to 0, go up, and 4 go to the right, heading there. Index 4 we have 3, 1, 5, right? 3, 1, 5, as we say. 5 we have 2, right? And going to the left is 4. So this is our direction, right? So our inner state, this is gonna be a list, right? It's gonna be a whole list. So for R in range 2, we're gonna do 2 by 3. So for column in range 3, right, we add to our init state. We just convert the current matrix to a one-dimensional array. So it's gonna be string of the board, right, column, just like that. Then we will have our init state, which is gonna be a join of the init state list right here, right? We have our index. Let me just write it out. So your index of 0, which is gonna be the, we're just gonna use the simple index find function right here, right? So let's say if the problem just gave us what we want already. So if the init state is equal to the final state, we just need to return 0 because that is only one move, right? And then now we're gonna start doing the BFS function. So we have the visit, which is a set, q, which is gonna be a regular dq, q.append, right? We're gonna do init state. We pass out init state in there. Just put a bracket right there. We pass out our 0 index right there, and we pass out count, which is currently 0. And for our visit, we just add init state and a 0 index, right? So that means we already visit the index. I also need to have a helper function, which is gonna be a process swap, right? It would take the state. We have index 1, index 2, and then we convert that to a list because what we pass is going to be a string, and we cannot modify string, so we must convert that to a list. Then we do a quick swap right here. So index 1, what am I doing? Index 1, result, index 2 right here, and then we perform a swap. Right, in Python this come really handy. Then we just return join dot rest, so we turn new state, right? So now we start our regular BFS. So we have a while loop in here for in range of length q. So usually you don't ever need this loop. I'm just gonna do it anyway. So I have my current state, z index, and our current move, which is pop left. So for our neighbor in the direction, right, of the current 0 index, we have our new state, which is gonna be equal to the process swap of the current state with the index 0 and our neighbor, right? So if my new state is equal to the final state, we return move +1. And then in here, if our new state and our neighbor is in the visit set, just need to continue. Finally, we append what we need to do. So just copy right here, paste it down here, put the indentation. So this 0 index turn to neighbor, this one turn to init, this one is gonna be move +1. Same thing for here, this is gonna be a new state. Oh, oops, neighbor. And at the end, we just return 0 if we finished our queue and nothing is off. Right, so just trying to run that, see if it's work. Invalid syntax because I missed a comma right there. 0 index not defined because I named this index of 0, but I call it 0 index right here. So now it should be good. Yep. And basically we just need to, it would be, oops, and that would be really fast. Just gonna do a, for time complexity, but we're looping through the whole matrix. So it's gonna be n times m, and the space is also n times m. Just to make sure, I just want to run this analyst just to see the correct one. Maybe I'm wrong. Factorial. Oh god damn. Beautify the state. Oh, the factorial is because we have our state right here, because we have to handle our state too. Which we have a lot of state actually. We have the, because it's not just traverse to the board, we're holding a state value too. So is that times on the state that could possible. So that's why it's higher than the regular m times m. So hope you like the solution, and I'm gonna see you soon on the next video.